Here we go. All right. And you promised to remind me to end early, right? Oh, oh yeah. Good. Um, Test one, done, out of the way. Great work. And now, new chapter, chapter 3. Just rolling through the chapters here. So now, right, chapter 1 was kind of an introduction to some core concepts. And then chapter 2, we focused on lines, right? Ended on absolute value functions, which are just two lines put together, right? So nothing crazy. And so now in chapter 3, we build it up just a little bit more to polynomial and rational functions. Okay, so we'll start with polynomials, which you may or may not recall from, I don't know, an earlier math course, perhaps. Okay. But we'll review it all. Okay. And so section 3.1, we introduce power functions. Okay. Power functions are anything of this form. So if you have f of x as x to the power of p, notice that x is down here. Right? In the next chapter, we graduate to having the x in the power. Right? A little bit more complicated, exponential functions, but for power functions, the x is down here just in the base. Okay? And p is just some number. Okay? And so what's kind of fun is the toolkit functions, you can rewrite them all as power functions. Okay? And so here's an LFF, a little fun fact. Have I used the LFF abbreviation before? It's a little fun fact. There, an LFF. All toolkit functions, which we're kind of familiar with now, right? Or at least we saw the benefit of understanding the absolute value function, for example, and maybe recognizing a parabola, right? And so as we move through, we'll recognize a couple more, right? And so all toolkit functions are power functions. Oops. Which means that we can write them as f of x is equal to x to the p, where p is going to be some number. The first one is super boring. F of x equals 2 is just a horizontal line at 2, right? And so in f of x equal to 2, right, x is equal to 2 and p is equal to 1, right? You could rewrite it as 2 to the power of 1. That's super boring, right? Not even a variable, right? What if you have f of x equals x? Right? Again, right? X to the power of 1, usually we just drop the power of 1, right? And so x is equal to x, and the p in this case would be 1. I want to make a couple of notes on the powers. Usually we drop a power of 1. Okay, so usually we write x to the power of 1 as just x. And x to the power of 0 is 1. Anything to the power of 0 is 1. You can try it on your calculator, right? 3 to the power of 0, you'll get 1. And so those are good to keep in mind. I guess technically we could have written this as 2 times x to the power of 0 if you wanted to. That seems fancy. We won't do that. X to the power of 2 and x to the power of 3, those are kind of easily identifiable power functions, right? And so if we have f of x is x to the 2, and then f of x is x to the 3, x in this case is x, and p in this case is 2. X is x still, and p is 3. In this section, we're going to focus on these two functions, x to the 2 and x to the 3. So we want to kind of commit the shapes to memory. I think we've all got the x squared pretty well down, right? And as we saw in chapter 1, right, and what we'll see again today, is that any even power of x will behave the same way, right? It'll just get smushed or stretched. Smushed is not a technical term, is it? Right, but it'll just be some version of x squared, but it'll have the same overall shape. Same with x to the 3, right? X to the 3 has this shape. And so we have to remember that, because now all the powers, all the odd powers, will have the same shape. Okay? Whatever you need to do to remember it. How about the root of x? Rutabaga is what I don't know why, think of that. Here's another note. If we have the nth root of x, you can rewrite that as x to the 1 over n. You can try it on your calculator, right? I think your calculators have fancy roots, don't they? Maybe not. I can't choose my root. I have, oh, there it is. Over my x to the power of anything button in the shift function, I have a choose anything root. Let's see here. Oh, this might muck everything up here, but I'm looking at, where's my pen? Here. I'm looking at this little button here by the hex on mine. Do you have something similar on your snazzy new ones? Probably. Feel like yours are better than mine. Mine's old. So here, right, you can do any root. I suspect. I haven't actually tried it. Let's try it. Okay, so we have to do let's do the 4th root of 3. 4th root of 3, I get 1.316, blah, blah, blah. If you do 3 to the power of, and then in brackets 1 over 4, I get the same answer. So you can try it with this button. Let's see here. But when you're working with just a regular calculator, right, not a fancy one like we have, right, then you usually have to do the x to the 1 over n to do any nth root. But what does that mean? This is a power function again, right? N is just some number, right? The 2nd root, the 3rd root, 4th root, 5th root, right? So 1 over 2, 3, 4, 5, they'll all be just numbers. So if f of x is x to the, I guess this is specific to the square root 1/2. X is still X, and the P is going to be 1/2. Same deal with the third root of X. We get the cube root, which we can rewrite as f of x is x to the 1/3. X is x. I don't know why I started writing the x portion. It'll always be x. But p is 1/3 in this case. So those powers that we're interested in, p's. How about these last two? The reciprocal and the reciprocal squared, 1/x, 1/x squared. All right. Final note about powers. Where can I put this? Maybe. Uh-oh. Now I've made a mess. Oh boy. Undo. I'll put it here. That's a bad spot, I think. 1/x to the n is the same as x to the negative n. You can rewrite it as x to the negative n. If you float it upstairs is kind of how I think about it, then you can make the power negative. So in this specific case, we have f of x is x. Technically, I have x to the 1 in the denominator, right? And so now if I float that upstairs, then I get x to the negative 1. And so this looks like x to the negative 1. X to the is x, and p in this case is -1. Power is -1. For the last one, the reciprocal squared, this is, now I have a power of 2 in the denominator, and so to bring it upstairs, I have to make it -2. X to the -2, x is still x, and p is going to be 2. So all of these can be rewritten as power functions. That's nice. Okay. So like I said, we're going to focus on kind of x squared and x to the 3 and all their siblings, cousins. I think they're siblings. They're so similar. Right? So here, if we look at the graph of f of x squared, right, that's this extra wide one, then what happens as I increase my power? X to the 4 is going to be this green one, which is a little bit tighter. X to the 6 is even tighter, right? And so it's increasing faster, right, as we increase the powers. But notice the general shape. The general shape of all these even powers, as we've seen, right, is the same. So notice the general shape of graphs for even powers is the same. How we can say that in a fancier way is that they have the same end behavior. Because just in general here, right, we've got a little bit of the x squared is pretty wide, and then x to the 4, x to the 6, right, gets tighter and tighter. But in general, as you increase your x, right, going to infinity, they'll all go to positive infinity. And same thing, as you increase your x and you, or I guess decrease your x and you go to negative infinity, then this arm, right, is going to shoot to positive infinity as well. right? And so the higher the power, it's just going to get to infinity faster, I guess. But they'll all get to infinity eventually. So this means they have the same end behavior. Behavior. So when we talk about end behavior, right, we kind of ignore what's happening here in the center, and we're really just talking about as x goes to positive infinity, right? Which means I'm heading out this way. So x going to positive infinity takes me out this way. Then we say that f of x is the output, right, on the y-axis. Now f of x in this case is also going to go to positive infinity. Right? So then it goes towards infinity. So we use these little arrows, right? And we say as x goes to infinity, right, f of x goes to infinity. And as x goes to negative infinity, what are we doing? We're heading out this way. So as x goes to negative infinity, what happens to the outputs? Well, even on this arm, right, as you kind of move out, you're heading towards positive infinity again. Right? So f of x is going to go to infinity again. I should have practiced my infinities. They always look bad. Wonky. So when we say they have the same general shape, right, what we really mean is they have the same end behavior, right? And depending on, what manipulations we've done, right? Maybe we've multiplied by some factor, and maybe we've moved it up and moved it down, or moved it to the side, right? Flipped it upside down. That's something to be aware of, right? Because then what would happen if we had a negative in front of the x to the 6, for example? It would get flipped down, which would change the end behavior, right? Now you're going to negative infinity instead of positive infinity for your outputs, but same for both x going to positive infinity and negative infinity. We'll see an example, so that's why I'm not writing it down. Not terribly surprising now that we've seen for the even powers. For the odd powers, it behaves the same as well, right? We see the same end behavior. So for example, if we start at x to the 3, I'm ignoring x to the 1. I'm not really calling it an odd power, because x to the 1 is just going to be a line, right? So it's kind of a special case. But starting at x to the 3, x to the 5, x to the 7, what happens? It's just kind of taking x to the 3 and making it a little bit tighter, right? Sending it to infinity just a little bit faster. In fact, positive infinity, as x goes to positive infinity, and as x goes to negative infinity, right, the outputs are heading towards negative infinity, right? Which is different from the even powers. So odd powers have the end behavior that as x goes to negative infinity, I guess I did positive infinity. Let's keep the same. As x goes to positive infinity, and so really what you want to do is you want to take your x's and kind of increase them, move them towards infinity, which is just to the right, but following the line instead, right? F of x is going to go to positive infinity. But as x goes to negative infinity, right? So now I'm on the negative x-axis, then the outputs, f of x, are going to go to negative infinity. Nice. So now, knowing that, right, kind of keeping in mind those two general shapes, right, just two shapes that we need to keep track of, okay? We have to describe the long run behavior of each function. F of x is negative, negative 2x squared. We know what the negative does, right? The negative is going to flip it on the x-axis, right? And so that's something to be aware of, you know? But in general, we might have a multiplier on here, right? That's okay. The same general shape applies, but now it's been flipped, right? And so here, this means it's flipped on the x-axis. So let's do A first. This is where it's going to be really helpful to remember kind of the general shapes, right? So if we take x squared, let's start there. And we have this parabola there. When I flip this, I have to flip it. Oops, looks wonky. On the x-axis. And the 2, I can't remember if the 2 makes it tighter, probably, because it's moving faster. Stretches, compresses. You've seen those, I don't know, comics, I guess. It's like my favorite dance moves. It's all the shapes. For simplicity, I'm just going to label this f of x is negative 2x squared. Let's pretend I did it. I applied the 2. Actually doesn't really matter in terms of explaining the end behavior, right? And so now, right, this negative is the important part. But knowing the general shape of x squared, we know that a flipped version of x squared is going to go to negative infinity instead of positive infinity. So as x goes to infinity, f of x is going to go to negative infinity. And as x goes to negative infinity, f of x will still go to negative. Nice. Remembering what the general shape of x to the 3 looks like, right? I kind of ignore the 3. I'm looking out for negatives in front, right? Because if it was negative, right? Well, let's start, I guess, with the default. Something like this. F of x is 3x to the 3. What would the negative version be? You still have to flip it on the x-axis. I just find this one is a little bit harder to visualize, but it'll look like this. If you wanted to talk about f of x is negative 3x to the 3. Let's do both. So for f of x, 3x to the 3, as x goes to positive infinity, f of x. So if we're looking at the positive version, right, as x goes to positive infinity, I'm heading up towards positive infinity. Oops. And as x goes to negative infinity, that little guy is going to shoot down to negative infinity. As opposed to if f of x is negative 3x to the 3, then this thing would look like, and maybe I should color coordinate a little bit there. Wow. As x goes to positive infinity and as x goes to negative infinity, right, having an idea of these general shapes. So as x goes to positive infinity, I'm heading down to negative infinity, right? And so f of x is going to go to negative infinity. And as I'm heading out the negative x-axis, I'm heading up to positive infinity. F of x is heading towards positive infinity. There. Nice. These are the versions, or kind of all the versions that we could possibly see. That's nice. So the textbook does call it long run behavior, right? Or I call it end behavior, and I can't seem to shake it. I just wanted to point that out because, oh, that's what I wanted to say. So hopefully you got my assignment, or sorry, my announcement, my announcement about the assignments. So they're unavailable. I don't know when it's going to be back up and running. And so, but of course, I can't get into it either. So once we're all back on, then I'll extend due dates and things like that. If you put a late pass on there, I'll extend that and just kind of bump it for however long it's out for. So you're off the hook for assignments for a little bit. And so it's on this new server and it's giving Steve some grief. So anyways, I'll let you know when it's back up and running. But I guess take some time off. That might be nice. You deserve it. It's probably been a busy week. Is next week as busy? I know. I shouldn't have asked. Next week will be better. Maybe. No. Just keeps going. Oh no. Oh no. I shouldn't have rubbed it in. It's busy for me too, but I'm kind of used to it and I know what to expect. You guys, you'll be jaded soon enough. So, oh yeah, that's what I wanted to mention at the beginning of class, but I forgot. So just hang tight, no harm, no foul. Everything will get extended, so don't worry. for those assignments. Okay, yeah, so if you are using the textbook to practice, there are problems in the textbook you could try if you wanted to, but I'm not going to expect you to, but if you wanted to, but he calls it long run behavior. Did I just blow your mind with a textbook? Is that what happened? Oh, you think I'm just kind of pulling this out of nowhere? Yeah, it should be on Moodle. It's just an open source textbook. So just a PDF. Um, I don't order them into the bookstore because I don't really see the point, but they're on Amazon. Or you can just use my notes, which is all I'm expecting you to have anyways. Okay. How about, it's been a while since we did some problem solving. Let's do it. Let's solve some problems. An oil pipeline bursts in the Gulf of Mexico, if you can imagine that. I guess, oh gosh. I'm still going to call it the Gulf of Mexico, I think. Causing an oil slick in a roughly circular shape. Okay, so you've got this kind of burst, and then it's increasing by some amount of time. So the slick is currently 24 miles in radius, but that radius is increasing by 8 miles each week. And so presumably it's just kind of pumping out, blah, blah, blah. If we wanted to write a formula for the area covered by the oil slick, we could do so by composing two functions together, right? Function composition. It's almost like there was a method to the madness, right? And so the first is the formula for the radius, which is r, right, of the spill, which depends on the number of weeks, and we'll call those w that have passed. Okay, so we're kind of given some variable information, and ultimately, what we want to find is the formula for the area. Bless you. Which it's kind of implied that it's going to be, or maybe it says, oh yeah, in a roughly circular shape, right? So we need to remember the area of a circle, right? The area of a circle, let's call it A pi r squared. Yeah, sound familiar? Now, it's not on your formula sheet, but if you need the area of a circle, for example, on the test, then I would give it to you, right? I would say, recall the area of a circle is pi r squared. So it's not something that I'm expecting you to remember, but you might remember it. What's a fancy way that you could write the area of a circle? Area depends on r, right? So it takes some input r. So really what you could do is you could rewrite this as a of r is pi r squared. But then r depends on w, right? The number of weeks that have passed. And so if we think about our oil slick, right, here we started, and look at that, kind of snaps into shape. R is 24 to start. But for each week, it grows by 8. Let's see if I can pull this off. With technology on my side, I just might. Okay, well, that's roughly circular. I'm using that to my to my advantage, right? And so here, another 8 weeks goes by, or sorry, 8 miles, another week goes by, I should say. And keeps going and going and going. So if you had to guess, maybe, R, the radius is going to be, well, we start with 24. And then for each additional week, we add 8. Right? And so I get 24 plus 8W. This isn't something that, you know, I think I think this is hard the first time that you're building this line. This is just an equation of a line, right? I've got one variable, we've got a slope, and we've got some intercept, right? And so that's kind of a stretch. But as you read more and more questions, right, you'll see, okay, you'll kind of start to see a pattern. Okay, it starts at this size and then it increases by this much for each week or for each minute or for each whatever, right? And so then you kind of get comfortable building an equation like this. Now, again, what's a fancy way that we could write this? R takes an input of W, right? And so really we could write it as R as a function of W is 24 plus 8W. Which means that the area of the circle, right, takes R as the input, but really what we want is we want to find A of R of W. And so what we want to find, A of R of W. So R of W is inside A of R, right? And so there we have a natural composition, right? Function composition. So here, this is a function composition. You don't need to call it that, but we have worked with those, right? F of G of X, right? And so that's why we had to practice kind of stuffing functions into another function. So what did we do when we had to build a function composition? Right? We start with A on the outside still, or I do. A of, and instead of R of W, I'm going to replace it with 24 plus 8W. Which tells me that in A of R, wherever I see an R, I replace it with 24 plus 8W. Right? Many of you might just feel comfortable going straight to that point, right? But technically, what you're doing is you're putting in R into A and then expanding. Yeah? Which means that pi, and then I see an R, which I'm going to replace with 24 plus 8W, then I have to square it. Okay. We're used to seeing X's, we've got a W, right? And we can expand this thing, right? Let's do that. Right? Just for some practice. How do you expand this thing? 24 plus 8W squared is 24 plus 8W times 24 plus 8W, right? And so you want to be really careful that you don't just expand the square inside because you'll miss some terms, right? I always have to write them out because I'm not very good at just seeing what the terms are. Okay, so what I mean by that is 24 plus 8W times 24 plus 8W. Right? Might remember FOIL, first, outside, inside, last. I don't find that that helps me terribly. And so that's why I have to just look at it and do it. I think you can call it feeding the chickens, but you'd have to do it twice. Right? And so either way, what do you have to do? You have to do 24 times 24 plus 24 times 8W plus 8W times 24 plus 8W times 8W. Keep that pi outside. Which is kind of fun to say, I guess. 24 times 24. Oh, and I say, I'll just make a note here that you have to multiply these. I'll use my calculator. I was gonna say don't be a hero, but then I hear it kind of. 576. Nice. So that's this guy here. 24 times 24. Now 24 times 8W. 24 times 8, and then the W just hangs tight. 192. Now I know 8W times 24 is still going to be 192, but I have to write it again. And finally, 8 times 8 and W times W. Let me just confirm here. I don't want to muck this up. 64 W squared. We can collect like terms, and maybe, just maybe, I'll write above here, just because we haven't expanded any squares, and we're going to see some cubes and things like that. So it's worth mentioning just this one time. But this was 24 times 24. This was 24 times 8W. This was 8W times 24. And this was 8W times 8W. That's where those came from. But I know a lot of people are just really fast at expanding. I'm not one of them. So you have to suffer through it with me. Okay. Keeping that pi on the outside still. Yeah. Pi, I like to keep pi as pi because pi is an irrational number, right? 3.141519, I think something. No, I don't know. 1.5. Yeah, there's a song, right? Yeah, there's a song. Got no quit. And we all trust that you're right. My sister bet someone that she could memorize more decimals of pi than this kid in high school, and I don't think she won because he memorized a lot. But she didn't memorize a lot. I should ask her. I don't actually remember. 192 plus 192. 384 W plus 64 W squared. All right, collecting those like terms of W. But what I meant to say is pi can just stay as pi. All right. And you've got a pi button on your calculator. Where is it though? Oh, it's above. It's good I brought this. On mine, it's down here above the times 10 to the x is a little pi. You have to go in the shift menu. They might have moved that forward, but on the new version. Okay. So we can multiply by pi if you want to. I would say that this is easier to do a calculation with. Why? Because if I am plugging in, 13 weeks later, right? Then I don't want to do 576 times pi plus 384 times 13 times pi, right? I would have to multiply by pi each time. Instead, I would prefer to just plug in w equals 13 in here and then multiply once by pi. Right? So that's what I would prefer. And so I'm going to leave it outside. Okay. I'll make a note of what I said though. I would leave pi on the outside to simplify future calculations. Of A of R of W. It's up to you. You can bring that pi inside. That works too. Oops. Pi is just a number. 576 is just a number. 384 number. W is a variable. Right? We're used to seeing x's, but here we have a w. That's okay. Right? And 64 is a number, and of course, and then w squared is still just a variable squared. Right? So when we have these variables here, and they're kind of linked together with sums, we call these polynomials. This is a polynomial. Oh. Let's see if I can peace. Poly means many, and nomials are the terms. Okay. We've got some terminology for polynomial functions. But a polynomial function is any function that can be written as f of x is a subscript 0, just meaning it's your first a, and so a is going to be a generic coefficient, plus a1 times x, technically to the power of 1, yet we usually don't write it, plus a2 times x to the power of 2, plus all the way up to a subscript n times x to the power of n. Right? So each power of x has its own coefficient. So here, what we can say is we can say, or even more kind of specifically, a subscript 0 is technically times x to the 0. I remember from the very beginning, x to the 0 is 1, right? A to the 0, or a subscript 0 times 1 is just a0, all right? Sometimes we call it a naught for null. A1 times x to the power of 1, technically, but x to the power of 1 we just write as x. And then plus a subscript 2 times x to the power of 2, plus a3 x to the power of 3, plus, and this just goes all the way up to some nth power. Okay. So usually we don't write the x to the 0 and we don't write the power of 1, but they're there. They're technically there. Okay. So let's go back here. I was gonna jump into something else, but so each of these a subscript i's, just a generic a, okay, they're constants and they're called coefficients, and they can be positive, they can be negative, they can be zero, okay? And so they can be whole numbers, decimals, fractions, they can be anything that you want. Okay? A term of the polynomial is any one piece of the sum. Okay? So if we look at the one we wrote out here, this is your first term, second term, third term, fourth term, nth term. I guess technically n plus 1th term, but that doesn't matter. Okay, so any ai x to the I is going to be called a term. Okay? Any individual term is just the power function. Right? We've seen those before. We can add them, we can subtract them, right? And so we know what each one individually looks like. It's just when we link them together, right, they'll have different behaviors. The degree of the polynomial is the highest power of the variable that occurs in the polynomial. Okay? So when you look at the highest power of the variable, right, we go to, well, here generically, it'll be the nth power, right? You go up to the nth power, but here, the highest power of w is 2, right? And so we would call this a polynomial degree 2, right? Because that's the highest power of w. We'll need to know the degree, because the degree of the polynomial, I know, spoiler alert, determines the end behavior of this thing. Right? And so that's kind of cool. We'll get there, but then the leading term is the term containing the highest power. So everything's kind of linked to the highest power of the polynomial. And so it's the term with the highest degree. And then the leading coefficient is the coefficient of the leading term, right? So that a. And so usually, right, because everything seems to be hinging on this leading term, right? The highest degree or the highest power is the degree of the polynomial, for example. Usually that's the one that we kind of latch on to figure out what this general shape is. Okay? And so for that reason, we usually write them so that the powers are descending. Okay? So we start with the highest power and we move down to the lowest power. So we rearrange them typically. To start with the highest power. So we can rearrange a of r of w, or if you want to just write it as a of r, that's fine too. We can rearrange this thing. I'll still keep the pi on the outside. You're welcome to expand it in. But like I said, it kind of simplifies things later. Pi tempted to divide by pi on both sides, but that would be weird. 576 plus 384 w plus 64 w squared. Let me scooch this here. Oy. Oy, oy, oy. W squared. Okay, fine. Because what I want to do is talk about. No, we can still do it. We can handle it. I want to talk about the degree. The degree of this polynomial. Now, I guess that's what I was going to do. I was going to rearrange these. I'll keep the pi on the outside. 64w squared plus 384w plus 576. This then is my, well, actually, technically times pi is my leading term. So my leading term, and I'll bump this up, trying to squeeze it on here. The leading term, remembering to expand that pi inside, would be 64 pi w squared. From that leading term, the leading coefficient is anything that's not w squared, 64 pi. Oh man, wrote that all weird. 64 pi. And then finally, the degree of this polynomial must be 2, right? The highest power of w. Even though there's a lot of activity here, right? There's more w's in here, this from this w squared, and then I've got 384w, and then I've got 576 in there, right? But the overall behavior, the end behavior, will be the same as w squared or x squared. Okay? In fact, let's do it. Can I pull it up? Will Desmos be happy today? I don't know. Pi times 64, I'll use x because I don't have a w, right? But it'll be on the x-axis. 64x squared plus 384x plus 576, end bracket. Well, what do you know? You can zoom this out, but it's just going to be parabola. Right? So that's nice. Looks complicated, but you know what the overall shape is going to look like. Oops, wrong tab. So we have to find the degree, the leading term, and the leading coefficient for these functions. Okay. As long as you're looking for the highest power for the degree, right? You don't have to rearrange them, but I think it's good practice to rearrange the polynomials so that the powers are decreasing, especially for later. We will do polynomial long division. I know, exciting, right? And so then it's going to be really important. So it is a good idea to rewrite polynomials with powers decreasing. So you just want to check, right? So I've got x to the 5 and then x to the 2 and then technically x to the 0, right? If you had to fill in the blanks here, right? What's actually going on here? F of x is negative 3x to the 5. That'll be our highest power. Right? What's not showing is that we have x to the 4 x to the 3. We do have an x to the 2. And then I don't have an x to the 1, but I do have an x to the 0, right? So technically what's in here is plus 0 x to the 4, because those coefficients are allowed to be 0, right? And that's how we make them kind of disappear. Plus 0 x to the 3 minus 3x squared plus 0 x to the 1, but usually we drop the 1. Okay. I'll do it on here. And then plus 1 technically times x to the 0. Right? X to the 0 is 1. And so 1 times 1 is 1. And so we usually don't write it. But if you had to expand it all out and show all these terms, but all these 0 terms, we tend to drop them. We wanted to find the degree, the leading term, and the leading coefficient. And I'm just going to copy that. Copy that here. The degree for this thing looks like it's 5. Highest power is 5. The leading term must be negative 3x to the 5. The leading coefficient is that negative 3. No? Now, what would the end behavior look like, this thing? Just looking at that leading coefficient, or the leading term, I should say. I have x to the 5, which I know the general shape of, right? Same as x to the 3. So like this. X to the 5. But I also have a negative coefficient, right? So that means I have to flip this thing. Negative 3x to the 5. Right? So just from the leading coefficient, and that's why we're talking about it. Okay, I wanted to just from the leading coefficient, wanted to do kind of dots in the middle, because we really only learn about the end behavior from that leading coefficient and the leading term and the degree, right? But here, x to the 5 would have this kind of behavior, end behavior. Anything can happen in the middle, right? As we'll see. Okay. G of x, 3 plus x to the 3 plus 4x to the 4, right? You want to look for the highest power. In fact, let's rewrite this g of x so we can see the decreasing powers, but also just for practice, let's also add in the missing terms, right? Those 0 coefficients, just so we can see that they are there, although they're being multiplied by 0. So I have 4x to the 4. I have an x to the 3, so plus 1 times x to the 3, technically. Right? Coefficient is 1. And then plus 0x to the 2 plus 0x to the 1 plus 3 times x to the 0, technically. From here now, of course, it's easy to see that the degree is 4. It's probably easy before as well. the leading term is 4x to the 4, and the leading coefficient is positive 4. So I know that the graph of this thing will look roughly like x squared. I'm allowing for some activity in the middle that I'm not committing to quite yet. Okay? But I know for sure what this x to the 4 graph end behavior looks like. Well, let's see if we get any sort of fun activity when we do it in Desmos. 4x to the power of 4, step it down, plus, is it 3? No, just x to the 3 plus 3. Oops. Oh boy, I'm all over the map. X to the power of 3 and then plus 3. Where is it? Okay, still kind of boring, but overall end behavior is still a problem. So the long run behavior, or what I call the end behavior, is going to match the long run behavior and behavior of the leading term, right? Just as we've seen. So describe the long run behavior of each of these functions. I'm gonna have to add a page here. Let's start with f of x is 3x squared minus 6x plus 1. I see that this is already written with my powers decreasing, and so that's nice. And so x squared, or 3x squared, what am I looking out for? I'm looking out for a negative in case there is one, right? Because then I need to remember the flip. Okay, but it's positive, so I've just got the behavior of x squared, which means that my graph would look something like this, right? Like a parabola. And so knowing that, and you don't have to sketch it out, but I find that it makes it easier to think about, right? Otherwise, you have to keep track of all these things in your head. That's hard. As x goes to infinity, right? No flip, then my f of x is also going to infinity. And as x goes to negative infinity, f of x is going to infinity again. Let's do B, where we have g of x is negative 2x to the 3 plus 4x squared minus 3. Keeping track of that, of the negative, right? X to the 3, we know what that looks like. And sometimes I find that it's easier if you just kind of do a quick graph of x to the 3 and then imagine it flipping. But if you're comfortable, oops. You can just start to sketch it out like this. So now, as x goes to infinity, g of x is going to, so as I move out on my positive x-axis, I'm going to negative infinity. And as x goes to negative infinity, then g of x is going to positive infinity. Nice. So it all hinges on the degree and that leading term. Aha. This looks like a mess. Uh-oh. All we really need, though, is the leading term, right? We need to know if it's positive or negative, and I need to know what the degree is, right? That's really all I'm looking for. So before we go ahead and expand this thing, right, just remember, you only need that first term, right, the highest power. So here, right, we only need the leading term. But if you're looking for something kind of soothing to do on the weekend, you could expand this, I guess. It's nice and relaxing. So we only need the leading term to find the end behavior. Which is good news for us. H of x, I'm going to write this out. In fact, I'm going to write the x minus 1 squared as x minus 1 times x minus 1, just to emphasize that you can't bring that square inside. Negative 2 times x minus 3 times x plus 4 times x minus 1 times x minus 1. That negative 2 times x times x times x times x, right? Which is really x to the power of 4 plus, who cares, right? Because now I know I have a parabola, flip down, right? And so I'm totally ignoring the stretch. Because that would be part of that kind of middle activity. Right? So here, the end behavior, as x goes to infinity, h of x is going to negative infinity. And as x goes to negative infinity, h of x goes to negative infinity again. Okay. Why am I doing these dots here? Because we don't really know what's going on with this thing, right? And so what if we plug this into Desmos? I'm hoping I know I'll get a good one this time. Let's see, I'll need to bring it in. Okay. Phew. Let's see here. I'll do the negative 2 times x minus 3 times x plus 4 times x minus 1. I'll do it squared. Finally, something with some action. What's the action? Well, okay, it's quite tall. It's going up to 200. So I'm going to zoom back out here. Woo, or try. Haha. Look at that beauty. The end behavior, though, is what we expected, right? Going down to negative infinity on both sides, right? But that's why I'm doing these kind of dots, dots in the middle, because we're allowing for some activity where it's allowed to go crazy and cross the x-axis and the y-axis and do whatever it wants. Okay? And so, but the end behavior is the same as what we expected. Let's see here. Bring that in here. All right. So that's kind of neat. Right? This end behavior as expected. Oh, nice. What about this activity? Uh-oh. This will be your short run behavior, right? So the short run behavior is going to be kind of all the action in the middle. Okay. And so characteristics of the graph, such as vertical, right? That's where it crosses the y-axis. That's a vertical intercept. And then we have horizontal intercepts where it crosses the x-axis. Okay. And the places the graph changes direction are part of the short run behavior of the polynomial. Okay. And so here, I'll bring that guy in here on the same page. I know, it's excessive. But it's also not real paper, so I'll go like this. So here, this is the short run behavior. So we can have horizontal intercepts, right? We can have vertical intercepts. We can have turning points, right? All that kind of fun stuff. Now, horizontal intercepts, we also call them zeros or roots of the function. So you might have heard the term zeros or roots, right? But those are all horizontal intercepts. In fact, here, the horizontal intercepts would be here, here, and here. I should use a different color, shouldn't I? How about orange? Aren't you glad I switched? Here, here, and here. So those are the roots or the zeros of the function, or the horizontal intercepts. How can we find the roots? Right? The roots, usually we call them the roots, or the zeros, I guess. Hey, went away. The roots happen when the output is 0, right? So all of these are when f of x is equal to 0, right? And so the horizontal intercepts, which we know already, zeros or roots, are the values of x where f of x is equal to 0, right? Or where y is equal to 0 if you want. So we can find the roots, right? Find the horizontal intercepts. But I think I have, I didn't have a note. What's the vertical intercept? The vertical intercept is here, right on the y-axis. Now, for a parabola, in order for it to stay a function, which it has to, right, I expect it to only cross the y-axis once, right? And so the vertical intercept the vertical intercept is where the function crosses the y-axis where it crosses the y-axis, that's going to be where x is 0. Right? So finding the vertical intercept is going to be, I think, the easiest part. And so let x equal 0, right? F of 0 is the vertical intercept. And like I said, in order for it to pass the vertical line test, it can only cross the y-axis at one point, right? And so there will only be one solution, whereas these roots or the horizontal intercepts, we can see that we're allowed to cross at multiple points. If I'm feeling very nice, which often I am, for finding things like the horizontal and the vertical intercepts, I'll give you a factored polynomial. So this is a factored polynomial. You could, for another soothing weekend activity, you could expand this if you wanted to, and it would generate a polynomial, right? But a factored polynomial is going to be easier to work with for finding the graphical attributes. Huh? Why? Let's start with the vertical intercepts. Why is that the easiest part? The vertical intercept, we said, is just we let x be 0 and figure out what g of 0 is. So let's start there. The vertical intercept is going to be g of 0. 2 times 0 minus 1 times 0 plus 3 times 0 minus 2. I don't actually know what that is, but 2 times -1 times 3 times -2, I get 12. Yeah, sold. So when x is 0, y is 12. That one's always the fun one, right? What about the horizontal intercepts? Horizontal intercepts, or the roots, if you prefer, or the zeros, I guess. I gotta stop writing out all the different options, but I think horizontal intercepts might be nice. The horizontal intercepts, we said, are the values of x where the output becomes 0, right? And so what's really nice, if we have this factored polynomial, what you can do is, I'm going to rewrite it here. G of x is 2 times x minus 1 times x plus 3 times x minus 2. Now from here, if this term is 0, because they're all being multiplied through, the overall thing just turns into 0, right? And so what would make that 0? X equals 1. First one, done. Or got it. And new color, who dis? X equals 2. So you can move through and force each component to be 0 right? And so what that means is at x equals 1 or -3 or 2, I know that I'll cross the x-axis at these points. Okay. And if we had to sketch this thing out, right, there's some other stuff that we don't know, but we have a pretty good idea. The only thing we need is to know the end behavior, right? And so let's add that on here. The end behavior relies on the leading term, which would be 2 times x times x times x. It's positive 2x to the 3. Okay. And so the leading term is 2x to the 3. Okay. Kind of take each of the first terms and multiply them through. Okay, using this, we can sketch the graph. There are some things that we don't know, but we can do a pretty good job. A pretty good job. Positive 2x to the 3. Let's start with the end behavior. I know should look something like this. What else do we know? I guess I'll do. Uh-oh, I've already used so many colors. I'll do the horizontal intercepts in pink. Because I'd say they're kind of the hardest. Now we're just sketching this thing out. So roughly here at negative, or maybe I'll do it out here. Here. -3, then at 1, and then at 2. So by that, roughly 1, roughly 2-ish. Right. We'd want graph paper or something to make it proper, but we're just getting an idea of this thing. We also know that it has a vertical intercept, so when x is 0, y is 12, which puts me, I don't know, somewhere way up here. Let's say here, I'm at 12. Okay. There's a couple of different ways that I could have these things cross, right? But I feel okay sending something up here and maybe up here and then maybe up here and then sure send it down here and then send it up that way. I'm doing dots just because we don't know, but that seems to be a reasonable sketch to me. Right? That's fancy. Huh? We can check it. Let's see how far off I was. Well, I kind of bungled it. Here. But let's see. Where's it? Here. Oh, it was a different one. 2 times x minus 1 times x plus 3 times x minus 2. We did not bad. Oops. If I can zoom in here, it does dip down just a smidge. Can I do? I want to emphasize that dip. Not bad. I'll bring it in. I think that's pretty cool and pretty fun. Incorporates a lot of things that we've learned. So does make for a nice test question. Right? But just like we did here, right? I'll just be looking for kind of a reasonable guess at the general activity, right? Nothing particular. Okay. Focusing on the end behavior and of course the horizontal intercepts and the vertical intercept. Okay. Let's see here. So what did I do here? I made the turning point at the vertical intercept. That's not necessarily the case as we see here, right? It kind of took a turn, a downward turn before it hit the vertical intercept, right? And so that can happen. That's okay, right? We're just doing a general sketch. Okay. So a polynomial of degree n is going to have at most n horizontal intercepts. Okay? And so an odd degree polynomial will always have at least one. Okay? Why doesn't it say that for the even degrees? X to the 2, x to the 4, right? If you think about those parabolas, what if you've moved it up? Then you have how many horizontal intercepts? 0, right? That can happen. Or the alternative is if you do have a horizontal intercept, then you would have 2, or if the parabola is just on the, where was we had a graph of one here. This looks like it's a parabola on the x-axis. That would just count as the one time. Okay. So then you would have only 1, but that's kind of a special case. Okay. So I guess it's true. All degree polynomials will always have at least 1. But anyways, whatever. What we'll latch on to is the at most n horizontal intercepts. Right? And so here we had a polynomial degree 3. And so my n is 3, and I'm allowed to have at most 3 horizontal intercepts. And I'm going to have at most n minus 1 turning points. Now, okay, we'll just do 3.1 today. A lot more. Quadratics. Save it for next week. Everyone likes quadratics. I think Frank already did some quadratics. You guys? Mm. Okay. Okay. Well, you've seen it. You'll see it again. What's the least possible degree of these graphs? So you want to start with kind of a jumping off point. Okay? And so here, this from the end behavior, this looks like some version of x to the 3. Right? And so we can start with kind of x to the 3 question mark, right? Because we want to find the lowest possible or the least possible degree. Okay? Now, when I look at the number of turning points, that might be a nice place to start. I have a turning point here, right? So a turning point is, of course, where it kind of bends. And so I have 1 turning point and another turning point, right? And so I have 2 turning points. Okay. I'd say that still checks out with n minus 1. So if n is 3, then I'm allowed to have at most 2 turning points. So I'm still feeling pretty good about this. Okay. What about the at most n horizontal intercepts? Okay. I've got 1, 2, 3, 3 horizontal intercepts. I would say the lowest possible degree of this thing is 3. Degree 3. There's clearly some other terms in the polynomial, right? An x squared or an x or just a kind of a coefficient, adding some short-term behavior. But the overall degree, the lowest possible degree that I would expect here would be degree 3. For the next one, you want to start with kind of a guess and then adjust your guess as you go. But I would say, well, this looks like an x squared, right? Parabola with some action in between, right? And so what I want to do is I want to check the turning points. Here I have a turning point. Here I have a turning point. And here I have a turning point. 3 turning points. But I'm allowed at most n minus 1 turning points, which means my degree must be at least 4, right? And so therefore, the degree is at least 4. We'll check the horizontal intercepts just to make sure that we don't need to up the degree. But when I look at the horizontal intercepts, there's only 2 horizontal intercepts, and I'm allowed at most, I had to up it to 4 horizontal intercepts, and so I'm gonna lock it in degree 4 for this guy because of the turning points. The lowest possible degree is what I should say here. Least possible degree is 4. Well, this doesn't look like least. Okay. You can try a fun quadratic example if you're looking for something to do. I can't remember what I was going to say here, so we'll leave it for next week. Anyways, we'll see if we can crack open that lab for you guys. If you have any questions, let me know. Enjoy your weekend. I'll stop this.